One special type of vector field is a conservative vector field. So a vector field F is conservative if it is the gradient of a scalar function, little f. In other words, capital F is the gradient of little f. So the gradient is a vector field because the gradient of f, say at x, y, and z, is going to be a vector, which is the derivative of f with respect to x at x, y, and z, the derivative with respect to y at x, y, and z, and then the derivative with respect to z at x, y, and z. So at every point, x, y, and z, we have a vector associated with that point. That gives us a vector field. In this case, though, this is a very special vector field because it is the gradient of another function. Now that function f we call a potential for the vector field capital F. Sometimes it's called a potential function. So a question that you would naturally want to ask is how do you show that a vector field is conservative? Well, of course, a conservative vector field would lean to the right. Hopefully there was some laughter in that awkward pause, but of course I was kidding. If we want to show that a vector field is conservative, okay, we want to show that that vector field must be the gradient of some function f. So if my vector field capital F, which say is PQ, we'll just do it in 2 dimensions, okay, is conservative, then it must be the partial derivative of f with respect to x and the partial derivative of f with respect to y. But in that case, I should be able to take the partial derivative of f with respect to x and then y, and then I should know that that's going to equal the partial derivative with respect to y and then x. So we've seen previously that the mixed second partial derivatives for our function f are equal. Well, if my vector field is conservative, then I should be able to take the partial derivative of the first component p with respect to y, and it should equal the partial derivative of the second component q with respect to x. So that gives us a template for how to show a vector field is conservative. Okay, we can take the partial derivative of the first component with respect to y and then test to see if it's equal to the partial derivative of the second component with respect to x. So, for example, let's look at the vector field f of xy is equal to negative y and x. So the function p is negative y and the function q is x. Well, in this case, the derivative of p with respect to y is negative 1, and the derivative of q with respect to x is 1, and those are not equal. So we don't have a conservative vector field. Okay, now let's look at our next vector field, g of xy. Here, the first component, p, is equal to x squared minus y squared, and then q is equal to minus 2xy. So I'm going to take the derivative of p with respect to y, and then I'm going to get negative 2y. And then I'm going to take the derivative of q with respect to x, and I also get negative 2y. And so because those are equal, we have a conservative vector field. Now, once we have a conservative vector field, now we need to find a potential function, a function whose gradient is this vector field. So what I'm going to do is I'm going to integrate or find the antiderivative of p with respect to x. Because p is supposed to be equal to the partial derivative of f with respect to x. And we also recall that q is equal to the partial derivative of f with respect to y. So I'm going to integrate this first function p with respect to x. If I do that, okay, my antiderivative of x squared is going to be 1/3 x cubed minus xy squared, and then plus a constant, because we always add on a constant when we find an antiderivative. But that constant is not actually just a constant. It's a constant that could depend on y. It's actually a function of y. And the reason for that is that if I take the derivative of f with respect to x, okay, so if I check, right, the derivative of f with respect to x is going to be x squared minus y squared. And then if I take the derivative of any function of y with respect to x, I will get 0. So this gives me a candidate for my potential function. Well, now I'm going to take the derivative of that candidate for the potential function with respect to y. And that, if I do that, is going to be, well, the derivative of the first term, 1/3 x cubed, is going to be 0. So I'm going to get a minus 2xy plus c prime of y. But I know that that derivative of f with respect to y is supposed to equal q. So that's supposed to equal negative 2xy. So that tells me that c prime of y must be 0. And that in turn tells me that c of y, my function of y, a function whose derivative is 0, is just a constant. Okay, so my potential function for this vector field is going to be 1/3 x cubed minus xy squared plus a constant. And now if you find the gradient of that function, you should easily see that it's equal to x squared minus y squared and negative 2xy. So these potential functions are not unique. They are unique up to an arbitrary constant, much like antiderivatives were when we were dealing with single variable calculus. So take that into account, because if it says to find a potential function, then you can let that constant be 0 if there's an arbitrary constant there. But if it says to find the potential function that satisfies some other constraint, you may need to find that constant. Okay, let's do one more example. And then this example is going to actually be my gravitational field from the previous video. So h of xy is minus x minus y divided by x squared plus y squared to the 3/2. Another way to write that maybe is, this is minus x times x squared plus y squared to the negative 3/2, and then minus y times x squared plus y squared to the negative 3/2. Okay, so that's my function p, and that's my function q. So I'm going to take the derivative of p with respect to y. I don't need to use the product rule because x is a constant in this case. So I'm going to get, let's see, 3/2 x times x squared plus y squared to the negative 5/2. And then I'm now going to take the derivative of the inside with respect to y, which is a 2y. Now I'm going to take the derivative of q with respect to x. Again, y is constant, so I don't need to use like a product rule or anything. This is going to be 3/2 y times x squared plus y squared to the minus 5/2. And that's going to be times, say, 2x, taking the derivative of the inside there. And hopefully you can see that these two functions are actually equal. And so, therefore, we have a conservative vector field. So now that we have a conservative vector field, I want to find the potential function for this gravitational field. Okay, so I'm going to remember that f is going to be the integral of p dx, so the antiderivative of p dx. So I need to find the antiderivative of minus x times x squared plus y squared to the minus 3/2. And so, in fact, an antiderivative of that is going to be x squared plus y squared to the minus 1/2. Okay, that's the same thing as 1 over the square root of x squared plus y squared. So let's double check, okay? If we check that, f sub x is going to be minus 1/2 times x squared plus y squared to the minus 3/2 times 2x. And then hopefully you'll see that the 2's cancel. And so I do get minus x times x squared plus y squared to the minus 3/2. Okay, so I've found my antiderivative there. Okay, but I need to have a plus c of y. So here I have plus c of y. It's very important that I don't forget that. Okay, well, I'm going to take the derivative of that function f with respect to y now. I'm going to get negative 1/2 times x squared plus y squared to the negative 3/2 times 2y plus c prime of y. And I'm going to set that equal to q. Q in this case is going to be minus y times x squared plus y squared to the minus 3/2. So hopefully you notice that this and this, in fact, match. And so that tells me again that c prime of y is 0. So c must be a constant. So a potential function for our gravitational field is 1 over the square root of x squared plus y squared plus c. Now I will warn you that in both of these examples, c prime of y ended up being 0, and so c ended up being a constant. But this is not always going to be the case. So as you're going through various problems where they asked you to find a potential function, be aware that c prime of y could end up being a function of y, and that then you'll have to integrate that in order to find c.